So now that we have a pretty good idea how floating point numbers work, especially in this little toy problem, this little 8-bit problem, we're going to look at what you do if you want to actually add or subtract these numbers together, right? Because it's not just about representing floating point numbers, it's about manipulating them. We want to be able to add floating point numbers. We want to be able to multiply floating point numbers. In fact, when you measure the performance of a computer, you're talking about flops, which are floating point operations per second. How many times can you take two floating point numbers and add them together or even multiply them? And what we'll find is actually for floating point numbers, multiplication is a little faster and a little easier than addition. However, what we're talking about is floating point operations. So what do they look like? How do you take two floating point numbers that are represented in binary and operate on them? When we had integers, it was easy, right? We just had integers and we operated on them. We had a little machine, this little full adder that would just add them together, right? Just recently we figured out how to make that efficient using the carry look-ahead adder. Have a look at that video. But here we want to take floating point numbers and manipulate them. So it's not a matter of taking those 8-bit strings and just adding them or subtracting them, because they don't represent numbers in the same format, right? The numbers in the significand represent different powers of 2 depending on the exponent. And so we have to actually take them apart, to line them up, and put them back together again. So here's an example. If we have, my pencil went away. If we have two floating point numbers, 1.1110 times 2 to the O, plus 1.000 times 2 to the negative 3, say, for example. What this represents is 1.110 plus 0.0001, and the result should be 1.10.000. So we get 2, right? This is 1 point something, and you add something else, and you get 2. So to actually do this math, first thing you have to do is normalize, put the two numbers together, right? So that, for the result anyway, when you're storing the result, we have to normalize. We have to put the two numbers together in such a way that when you do the math, you might not get the same exponent, right? Which exponent are you going to use anyway? Here, we're going to normalize. We're going to move that one back, and then the number we're actually representing is 1.0000 times 2 to the positive 1. Right? So even if we could take two numbers and add them together, the result may not fit in that representation. So we have to shift things around to normalize it so that it fits in the representation. Same thing with subtracting. We could have, 1.111 times 2 to the 0 minus 1 times 2 to the negative 3 gets us 0.111, which again is not normalized. So we would have to shift it around to make it 1 point something. That's not right, there's too many ones here. 1 point something times 2 to the negative 1. But this even asks a different question, is these representations, right? We're not actually adding these numbers and these numbers. We have to denormalize them, deconstruct them, put them into their component parts first, so that whatever machine we're going to use can actually add them together in the same place values. So this is also going to bring up, now that we're manipulating numbers, some special numbers, some different numbers that we are going to need to find out some special way to represent, because what we'll find is that without this specialization, there are some really important numbers that we can't actually use. To that point, when we normalize, meaning what we're representing is 1 point something times 2 to the something, we can never represent the number 0. Because all numbers have value. That 1 is baked into the representation, and so we can't represent the number 0. Now, I don't know about you, but I use the number 0 an awful lot. When I'm comparing two numbers and deciding what to do, often I want to say, is this number negative or positive? Is it bigger than 0 or smaller than 0? Now, in the representation, we have that negative sign, we have that positive sign, but there's a lot of other situations where we want to use the number 0. So we're going to need a special way to represent the number 0. And what we do is we take the largest exponent and the smallest exponent. The smallest exponent being 0, 0, 0, corresponding to negative 3, and the largest exponent being 1, 1, 1, corresponding to positive 4. We take those two exponents and we reserve them. We say, you know what, if we get a number that's this, that means something special. In the first case, here are the special numbers. If the exponent is 0, meaning -3, then we're not saying 1.0 times 2 to the -3. We're saying this corresponds to the special number 0, which otherwise we couldn't represent. When the exponent is the biggest number, we're going to use that to represent two other special cases. One where the result is infinity, because that's a special number. If we're going to represent 0, we might as well also represent infinity. And another where we're going to represent something called not a number, or nan. That nan is a result that the computer can give when you try to do an operation that doesn't make sense, like, for example, dividing by 0, right? Or getting a number that's out of range, or who knows what. There's lots of situations where you want to be able to report back to the system that the result you got wasn't a good result. So we use not a number for that. So 0, infinity, not a number. These are three special numbers. And we represent them, again, this is the toy problem, an 8-bit problem, but we use exactly the same representation for the full 32 and 64-bit IEEE numbers. If the exponent is all zeros, that represents 0. If the exponent is all ones, that represents either infinity or not a number, depending on whether the significand is all zeros or not. If the significand is something other than all zeros, then it's not a number. If the significand is all zeros, then we use that to represent infinity. Now, you're probably looking at this and saying, well, there are 4 cases here, not 3. What if the exponent is 0, but the significand is some number other than 0? Well, that's the 4th class of special number that needs a little bit of extra work called denormalized. And we'll do that in the next video.